and we will talk about dynamic optimization, a variant of particle swarm optimization. So this is some work with our colleagues. So let us start with a short outline. So first we will talk about the motivation problem statement, then some related work. Then I'll tell about the proposed approach and some experiments, and at the end we'll have a conclusion. So first of all, let's talk about the dynamic optimization problems. So what are they? In many cases, we usually consider that our optimization problem is static. So we have our f of x, some function that we should optimize. We should find the minimum or the maximum of this function, and that's it. So this is the problem to be solved. But in real life, often these kind of problems are changing over time. So they need to be solved online. So solved like many times, and these kind of problems that are changing are called dynamic optimization problems. So these are obviously black box optimization problems if we're talking about evolutionary computation approach. And the good news is evolutionary algorithms are actually somehow well designed for these kind of problems, as the evolution itself it exists it happens in dynamic environment. So somehow it is logical to use these kind of population-based algorithms for dynamic optimization. So let's state the problem more formally. So we need to optimize f of x, phi, and t, and our x is a function which belongs to some set of function, and t is time. So phi is a set of parameters of the environment. So we have our search space, we have time, we have search space dimensionality d. So we need to optimize this function at every moment of time, find the optimum. Where can we find such kind of problems? So here you can see a list of classical problems where you can find this dynamic optimization. So this is usually some kind of control problems, so connected to some processes that happen in real time, maybe some chemical processes or physical processes. So all these kind of problems that should be solved dynamically, this is where we can find them. Of course, the interest in dynamic optimization is growing. This can be seen by the number of publications in recent years. But as I mentioned in my previous talk today, it is interesting to see that this year in 2022, there were 4 competitions on dynamic optimization. So two of them were on dynamic multimodal optimization, one on just dynamic optimization, and one on dynamic stacking problem. So this is obviously some trend, some interest is in the field of dynamic optimization. So this is somehow a hot topic, I would say. So why actually we need to consider dynamic optimization problem as a challenging task? Well, of course, every optimization problem could be challenging if it's complex, if it's big enough, but there are special difficulties in the dynamic case. So usually the dynamic optimization problems are modeled by several peaks, as you can see on the pictures on the right. And what is dynamic about them? Of course, the location of components or peaks may change. Their size, so how much space they take, the shapes of the components, they could be rotated. The number of visible optima may change, so one peak could overtake all other peaks, and also the optima could be ill-conditioned, and the components themselves could be more complicated than just like balls that you can see on the picture on the right. So on the bottom right, you can see the example of strand of one of the peaks. So it may change differently depending on the parameters that are in the benchmark that we consider. So it can change quite different. So in this study, we will consider the generalized moving peaks benchmark, which is the further development of the moving peaks benchmark. Obviously, this is modeling the peaks, so we can see in the middle the classical peak function, which is actually usually quite easy to optimize to find the optimum for this. But the GMPB benchmark adds several complications. First of all, there are many peaks, then there are irregularities, asymmetry, ill conditioning, and rotation. Some of the effects of all these things you can see on the right. So we could add irregularity, so there will be more optima. We could add asymmetry, so it will be biased. We could add ill conditioning, so the function will be stretched and also rotated. So the general form of the test function you can see here also on the bottom of the slide. So it includes some sine function, log exponent function, and many more. So what changes in this case? Of course, the angle, the rotation angle changes, the height of every peak changes, the width, the shift, and the irregularity of every peak changes. So in this case, in the case of GMPB benchmark, the positions and the parameters of all peaks, they stay the same for a short period of time, maybe 1,000 functional variations, then the environment changes. So all of these parameters listed, they are changed for all of the peaks. So it makes a different picture, but somehow still similar to the previous one. So what does it look like? You can see, for example, on the lower part of the slide. So even in two-dimensional case, this is quite hard optimization problem. Maybe even more difficult than we see in, for example, CEC or Gecko competitions. So now let's talk about approaches that are used for such kind of problems. First of all, we should say that the time period between different environments is quite short. So, for example, the algorithms based on differential evolution or genetic algorithms or some other methods, they are quite slow in the meaning that they are very careful in the search process. But the particle swarm optimization is not very careful, but it converges quite fast. So these kind of methods are very popular for dynamic optimization problems because of their fast conversion. Maybe they don't get the global optimum, but at least they get a good result. So, and one of the popular methods is so-called the MQSO, the multi-swarm quality swarm optimization method. So it's multi-swarm, so it uses a set of swarm. Of course, it implements standard PSO for each of them. Then it also has so-called exclusion. So if some swarm is converged, then it's excluded and generated again. Then anti-convergence, if several swarms are at the same peaks, then one of them is excluded and generated again. And also there is a local search with so-called quantum particles or charged particles. Yeah, so let's dig into more detail with MQSO. So on the left, you can see the standard procedure of the particle swarm optimization, which is applied also in MQSO. And in the original algorithm, for every swarm, there are several additional points generated with uniform distribution next to the best position of each swarm, next to the global best found. So this is kind of local search for the algorithm. And what we did is in this study is we tried to improve this local search with several modifications. So they're listed on the right side. So first of all, we decided to use normal distribution with zero mean instead of uniform for quantum particles. Of course, now they cannot be maybe called quantum particles, but nevertheless, we stick to the terminology. The standard deviation is set to this air cloud value. And this value is actually sampled with normal distribution with a mean of MR. So what is this MR? This is a memory cell similar to the whole idea of the method is similar to the success history adaptation used in differential evolution. So there are several memory cells, and at every iteration, the R cloud parameter is sampled from normal distribution, and if the sampled point is better than previous global best, then we save the R cloud value as a successful one, and we also save the fitness improvement. Next, at the end of every generation, we update one of the memory cells with Vladimir. So yeah, this is the idea. Let's return back to the benchmark. So of course the GMPB is a generator of test functions, so you could use it in the way that you like. You could say any parameters. But for this study, we used the parameters proposed for the CEC 2022 competition. Though we didn't participate in the competition, but nevertheless. So here there are 12 cases, 12 scenarios considered with different number of peaks, different change frequency, different dimension, different shift severity. So shift severity is how far the peak moves between different environments. So there were totally 100 environments for every scenario, and yeah, you can see the parameters of the algorithm that we used on this slide. So we set 10 swarms for each scenario, so the parameters were equal. We varied the number of individuals from 5 to 25, and also the number of quantum particles from 1 to 10. Memory size was 5, and we made 31 independent random. Also, we tried to change the shift severity by 5 times to see if the algorithm is able to adapt to this change. So yeah, finally, the evaluation criteria that we use is called the offline error. So how far are the global optima that we know where it is, and the best point found by the algorithm at every time step. So the sum of all these errors makes together the offline error. Also, we used the Mann-Whitney rank sum statistical test and calculated the standard score, Z values. So this is for pairwise comparison. You can consider them as the amount of sigma. So 3 sigma is significant difference. Everything below is not so significant. Okay, so these are the results of the first set of experiments. Here you can see 2 heat maps. So as I said, we varied the number of quantum particles, it's on the x-axis, and number of individuals in the population, it's on the y-axis. So the standard parameters are number of particles 5, number of quantum particles also 5, and you can see that on the crossing of 5, that score is 0. But we found out that if we increase the population size, even in the standard MQSO on the left part of the picture, the algorithm performance actually increases a lot, like very significant. It's actually for all, not for all, but for most of test cases, we got a significant improvement in performance. It's interesting because these 5 are recommended parameters, but it seems like nobody actually tried to vary them. On the right side, you can see the same effect, but with the MQSO SHA algorithm. And again, if we increase the number of individuals, the number of particles in the swarm, in the population, we get much better result. So there is some sweet spot around the population size of around 12 and around 5 quantum particles. So in the next experiment, we compared the MQSO and the MQSO SHA, so baseline and modified approach, and we used the same population size and the same number of quantum particles for both algorithms. So at every point, it's a comparison of baseline and modified version. So as you can see, for example, these 2 pictures are for standard shift severity and increased shift severity. On the left part, you can see that if we increase the number of quantum particles and the population size is relatively small, the modified algorithm becomes much better, because if there are many quantum particles, it mainly relies on them in the search. But nevertheless, even if we increase the population size, the proposed algorithm performs much better. And if we further increase the shift severity, which actually makes the optimization problem much harder, the effect of the modification is much bigger. So we get improvements for many test scenarios compared to the standard case with standard shift severity. So one interesting thing also to see is how the parameter adaptation actually happens. So we choose
Vladimir, we have lost your sound.
How about now? Can you hear me?
It's okay, yes.
Yeah, okay. As I was saying, different test scenarios result in different parameter adaptation curves. So for some scenarios, for example, with a lot of peaks, like 50 or 100 peaks, whereas we have only 10 populations, the spread of quantum particles is increased a lot. Whereas in other cases, when the number of peaks is smaller, we have smaller values of adapted parameters. So we can see here that yes, the algorithm actually feels what's happening, and it is able to react by tuning the parameters to the environment. So finally, here are some Mann-Whitney tests comparing the baseline algorithm and the modified. Of course, on most problems, the difference is statistically not very significant, except for the most complicated cases with big shift severities, big number of peaks, or small time between environmental changes. But if we again increase the shift severity, the modified algorithm becomes much better. So in conclusion, we can say that we've proposed the parameter tuning for the success history adaptation algorithm, and we have shown that this is an important modification. It makes a difference, and as I forgot to mention that it was indicated in the talk in Gecko about the dynamic optimization that the research on the parameter adaptation, this area is actually very small. So different algorithms are proposed, but most of them don't have the online parameter tuning. So this was our attempt to do something like this using the approaches taken from differential evolution. So that's it for this talk. So please, if you have any questions, I will be glad to answer.
Thank you very much. So please, your questions. Okay, as usual, I will start conversation. So my question is, it's clear that, how to say, the intensity of changes can be different. Can we somehow measure this value of changes and apply a special strategy for adaptation? For example, if it's very small changes, we can use a kind of local search for very simple and very fast adaptation. And in another case, it's much better to use such global search algorithm like multi-swarm PSO.
I see. So, in fact, the MQSO in the implementation that we originally used, it had the tools to estimate the shift severity. So how far is the previous peak compared to current peak? So how far did it go? But this mechanism, as it was implemented, at least it didn't work. So actually with shift severity of 1, it estimated that it is around 80. So it's 80 times bigger. I'm not sure why this happened, but obviously this doesn't work very well. So regarding the question if we can detect this, I think we can. Yes, at least we could track the parameter adaptation. We can see that, okay, the shifts are large. So maybe we could use some more global variant of PSO. So yeah, but this is quite a difficult problem. Yeah.
Okay, thank you very much.
Mm-hmm.
So if anybody would like to ask a question, you still have a chance. Okay, I think today we have very long and very hard session, so everybody would like to have a rest. So we will finish today session and we will continue tomorrow. You can see schedule on our website, so we will start at 3 p.m. Krasnoyarsk time. So see everybody tomorrow.